Hi everybody. In this video, we're going to look at concave and convex functions and how we can identify them from the second derivative of the rate of change of a gradient. If we begin with looking at y equals x squared, we'll look at this using GeoGebra. So we've got y equals x squared and we've got a tangent to the curve. Now if I move this tangent over to the left, watch how the gradient of this tangent changes for increasing values of x as we move to the right of a curve. Can you see that the gradient of a tangent is always increasing? If we go back over to the left, you can see that the gradient of a tangent is negative, but it continues to become less steep, or it continues to increase until it becomes positive and again continues to increase further. So the gradient of this tangent is always increasing as we move along the x-axis. If we go back to our notebook, so if the rate of change of the gradient continues to increase as we move along the curve, then we say that the second derivative is always greater than 0 because the gradient is always increasing. And we can see how this works. If y equals x squared, then dy by dx will be 2x, and the second derivative will be positive 2, and positive 2 is always greater than 0. Now we describe this as a convex curve. You can tell it's convex because if you join 2 points along this curve with a straight line, the curve is always below the line. So this tells you that it's always convex. Okay? If we look at y equals the natural log of x, again we'll go back to GeoGebra, you can see that the gradient of a tangent of a curve, as we increase the values of x, is always decreasing. It's always becoming less steep. Now it never becomes negative with this function, but the gradient also never increases. So if we go back to our notebook, so because the gradient is always decreasing, we say that the second derivative is less than 0. And again, we can see how this works. If y equals the natural log of x, then dy by dx will be 1 over x, or x to the negative 1. So the second derivative will be negative x to the negative 2, or 1 over x squared. And we know that x squared is always positive, so the rate of change of a gradient must always be negative. And we call this a concave function. So if you join 2 points on the curve with a straight line, you can see that the curve is always above the line. So this is concave. Okay? So as we progress through this video, we'll be applying these two ideas. If we look at example 1, we're given that f of x is x cubed plus x squared minus x. We need to find the range of values for which f of x is convex and concave. So if we work out the first derivative, this will be 3x squared plus 2x minus 1. We'll work out the second derivative, the rate of change of a gradient. This will be 6x plus 2. So it's convex when the second derivative is greater than 0. So 6x plus 2 must be greater than 0, so x must be greater than negative 1/3. And it's concave when the second derivative is less than 0. So 6x plus 2 must be less than 0, so x must be less than negative 1/3. And we can use these properties to sketch the graph. We know f of x must pass through the origin, because when x is 0, all of this becomes 0. So it passes through the origin. And if we look at the point when x is negative 1/3, to the right of this point, x is greater than negative 1/3, so this will be convex. It will look something like this. And to the left, when x is less than negative 1/3, the curve is concave, so it looks like this. So this is the sketch of f of x. So we've talked about when x is less than and greater than negative 1/3. When x is equal to negative 1/3, we have what's called a point of inflection. And this is where it changes between the two. We'll talk more about this in the next example. So a point of inflection is where the curve changes from concave to convex. So the second derivative changes sign. At a point of inflection, the second derivative equals 0. But not all points where the second derivative equals 0 are points of inflection. We need to check the sign either side of a point. So we've been asked to find the point of inflection for f of x. So the first thing we need to do is we need to differentiate with respect to x. And we get 3x squared minus 4x plus 1. We need to find the second derivative. This will be 6x minus 4. And at the point of inflection, this will equal 0. So 6x minus 4 will equal 0. X will equal 2/3. So we can show this about this point here, 2/3. To work out the coordinates of this point, we'll substitute 2/3 into our function. We get 2/3 cubed minus 2 lots of that squared plus 2/3. So y works out to be 2/27. So I'll label that here, 2/3 and 2/27. Now we need to verify that this is a point of inflection. So what we do is we pick a point on the curve either side of that point of inflection. So we'll say the point to the left will be 19/30, and the point to the right will be 21/30. And we substitute each of these points into the second derivative. So we've got 6 lots of 19/30 minus 4, which works out as negative 0.2. Then we'll substitute in the 21/30, and we get positive 0.2. So because there's a change in sign either side of a point, and at the point the second derivative equals 0, this is a point of inflection where it changes from concave to convex. Okay? Well, thank you very much for watching. I hope you found that useful. If you want more practice on this topic, you can download the worksheet and view the online lesson from my website, mrmathematics.com. I'll leave a link in the description below.